And in each trial, there are primary and the secondary endpoints. The primary endpoint should be based on the variable capable of providing the most clinical relevant and convincing evidence directly related to the primary objective of the trial. Then secondary endpoints are either using supportive measures related to the primary objective or measurements of effects related to the secondary objectives. Now here's one of FDA's guidance. For drugs approved in the US, the sponsor needs to demonstrate the drugs are safe and effective with substantial evidence in at least 2 adequate and well-controlled clinical trials. Sometimes the sponsor can only afford to conduct 1 trial. So when only a single adequate and well-controlled study is conducted to demonstrate effectiveness of a new use, pertinent information from other adequate and well-controlled studies of a new drug may be considered. So normally we require the sponsor to submit 2 positive trials for the drug's approval. Now I have listed some statistical hot topics. The first one is the study design, and actually this is something I worked on recently, which is enrichment design. And Chen talked about adaptive design earlier. And the second one this year is the determination of efficacy endpoint. The patient-reported outcomes actually is a very hot topic nowadays. They need to identify the right endpoint to do the trial. And so the topic I'm going to the example I'm going to show you later is related to enrichment design. And I also briefly touched on the multi-regional clinical trials. I had the research work earlier. And the third topic here is missing data control and analysis. Mark will cover that. And the next 2 is a study-wise type 1 error rate control in terms of multiplicity and subgroup analysis. So here is a slide showing you the enrichment design that I had done research earlier. So this is a sequential parallel design. It's an enrichment design. First proposed by Fava in 2003, and my colleagues and I had extended with re-randomization, and we published later in year 2011. And this is a design has 2 phases. The first phase, 2 stages. And the first stage, this is actually just a traditional parallel design. The drug will be the patient will be randomized to either drug or placebo. And the second stage, only those patients who are placebo non-responders will be re-randomized to the drug and the placebo. Okay, the motivation behind this is sometimes you observe high placebo response in some trials. So we want to use some kind of design to tease out those patients who are placebo responders to help the drug show the difference when compared with placebo. So the placebo is by far the mostly used control group in clinical trials. When the placebo response is high, the drug effect may not be easily differentiated. Therefore, some types of enrichment design has been considered to separate out patients who are placebo responders. However, one drawback of this SPD is the need to have patients in placebo for a long period of time, which may not be ethical, and you may encounter a lot of dropouts. So my colleague and I had thought about this, and we come up with another design. It's called the sequential enriched design. So instead of having a patient who put placebo for a long time, so we only study the patient who are in a drug, and those are drug responders. Then we have them re-randomized to the placebo and the drug. And notice that before the trial start, we add a placebo lead-in in front to tease out those placebo responders. Okay. In other words, the rationale of this sequential enriched design is our target patient population respond to a drug, but not to a placebo. A placebo lead-in phase is implemented at the beginning of the trial before randomization to screen out patients who will respond to placebo. And at the second stage, only patients who are drug responders will be further re-randomized and studied. So the next topic I'm going to talk about is some work I have done for the multi-regional clinical trials. Multi-regional clinical trial literally is some clinical trials conducted in multi-regions. So here is a famous Plato example. You can see the overall treatment effect. The study is positive with p-value 0.0003. Right? However, when you do a subset analysis, subgroup analysis, you'll see it looks like the drug maybe the effect only driven from the non-US data, not the US data. However, this drug will be approved in the US. So we are thinking, should the drug be approved in the US? How should we deal with this kind of problem? In year 2010, I also had an opportunity to work with my FDA colleagues to perform some meta-analysis using 33 schizophrenia clinical trials that were submitted to the agency. We found that on average, although based on this graph, you'll see the Eastern Europe and Asia occupy like 30% of data. However, if you see this forest plot, you can see actually the Asia and the Eastern Europe, that's the first two there. You'll see the treatment effect show the difference from the US treatment effect. Okay, so next Mark is going to talk about missing data.
Yeh-Fong had asked me to give an application, which I'm going to talk about, which is in weight management for missing data. I think I want to add something about FDA work to what Yeh-Fong said. We have this sort of campus now in Silver Spring, and it contains many of the centers, not all of them. And collectively, within the FDA, there's over 300 statisticians and over 260 at that campus. And there's a bit of flexibility, too, in the work. For example, starting this week, I started a detail for 4 months, comes with a temporary promotion, in the Center of Devices and leading a couple of teams there. Also, last year, I was part of a cross-government team with people from the Air Force, Office of Director of National Intelligence, and Interagency Council on Homelessness to put together onboard training for the Office of Director of National Intelligence dealing with social media awareness. So there's a lot of opportunities, so I'll make that plug. But what I'm going to talk about here is submission in which someone on my team gave a presentation at the advisory committee, and I took some of his slides. And the issue isn't whether this product helps to reduce weight, it works. The issue is what's the most appropriate estimate of its effect. And why this is relevant is because measurements are often not taken from subjects once they stop therapy. And with weight management products, including this product, when you're on it and then get off it, you tend to put on weight. So using what the sponsor wound up trying to do is to use the patient's last measurement on drug for weight change, and that tends to overstate the true effect. So there were 3 trials. I'll just concentrate on one of them. And I'm going to concentrate on the endpoint that is change from percent change from baseline in weight to 56 weeks. The sponsor's analysis just used on-treatment measurements and imputed forward the last available on-treatment measurement. For terminology, we call them subjects that discontinue therapy but come back and get measured for an endpoint, retrieve dropouts. And those that discontinue therapy and don't come back and get measured would be called non-retrieve dropouts. Missing data, particularly in the past few years, has been a big issue at the FDA. There wasn't enough done previously on having clinical trials, not have much missing data, and on what to do in the analysis in the presence of missing data. The FDA had a council form through the National Academy of Sciences. They put together a report that was published in 2010. One of the recommendations is, in essence, discouraging to use single imputation methods like something like a last observation carried forward. Oh, okay. I was expecting the whole picture. Yeah, we use somebody else's slides. Okay, so this is going to illustrate what typically happened for a retrieved dropout on the experimental arm. So they would observe some weight change, some weight reduction from baseline. They'd get off the treatment because they probably couldn't tolerate it, not because they didn't appreciate the weight reduction. And the weight change from when they got off treatment was carried forward to 56 weeks in analysis, but the reality was that they actually put on weight. And the measurement was actually taken at 56 weeks to show that they put on weight after they got off treatment. And this table just illustrates for that one study what happened. And this was a placebo-controlled study, background of diet and exercise. So there were 171 subjects on the experimental arm that had both imputed and actual weight measurements at 56 weeks. The imputed changes had a mean of reduction of 4.9%. The actual measurements are 3%, meaning they put on sort of that 1.9% in between. Placebo, they tended to still lose a little bit more weight, had more stable weight after they got off placebo. Now, part of this might be because these weight products do affect two things typically. They affect the brain, might make you a little happy. Some weight products have, one weight product that was approved was an antidepressant, and when you get off that, 3 minutes, okay, you know, things sort of change. All right. Now we like to do what's called intent to treat analysis. And there's two nice things about intent to treat analysis where you use all the randomized subjects and the actual measurements if you had them. One, you preserve the randomization, integrity of the randomization. And two, you have analysis that's relevant to when a treatment decision, initial treatment decision has to be made. Now then, to do that, to try to get an ITT type of analysis, what was the actual measurement of the subjects that we don't have measurements for? Well, one, we do use all measurements. And two, we're going to use sort of the retrieved dropouts in a given arm to help model what would have happened to the non-retrieved dropouts. And this shows sort of the amount of missing data and retrieved and non-retrieved dropouts. About 1/4 of the subjects that discontinued were actually retrieved. And we're going to do two types of analysis. One is a weighted analysis, which was our sort of second choice, where each retrieved dropout would represent themselves and the non-retrieved dropouts in the same arm, accounting for also the known measurements on the non-retrieved dropouts. So what happens when we do that? Well, when we do that, The overall mean change on experimental got a little worse than the sponsors. Instead of -8%, it's -7.4% from baseline. And on placebo, it got a little bit better. So the difference went from -5.4% to -4.6%. Not a huge difference, but a little bit decent sized difference, reduced the effect by about 15%. And I guess we felt it was more meaningful to use to describe the risk benefit, and so that patients and prescribers could really know what the true effect of the product is. So I'll leave it at that, because I'm out of time. Do I have 1 minute? Or?
You do have 1 minute.
Okay,
We'll
I'm going to move away from this for 1 minute. So I'll talk a little bit about Iowa and since, leaving Iowa, and I guess going to the FDA. I did get married. I met my wife at the FDA. I did get married in 2001. Had 2 people from Iowa who were my groomsmen, Hamu and Tony Chen. I proposed to my wife, who's from Taiwan, in Mandarin, and one of the people in the photos Hamu showed was Yeh bin Lian. And Yeh bin Lian told me the right words, Xinjia Ge Wo Ba. And I usually we have Thanksgiving gathering at my house where I do the cooking and have Iowa people, Yeh-Fong's regular visitor and her family, Nelson Liu, A.G. Ishida, and Terry Gurras was there this year, an occasional visitor, and Jerry Machinsky. So have had some continual interactions with my fellow Iowa graduates since leaving here. So I wanted to mention that. Okay.